Okay, let me start. So the title of my talk is Smooth Locus of Twisted Affine Schubert Varieties and Twisted Affine Demazure modules. This is joint work with my student Mark Besson. So first of all, let me start with some notation. So here G is a connected simple algebraic group of adjoint type over C. And so this another letter of G is the Lie algebra of this group. And T is the maximum torus of G. And this H is the Lie algebra of the torus, which is a Cardan subalgebra in the Lie algebra, simple Lie algebra. And one can define the Affine Grassmannian of G as a quotient, GOK by GO. So this quotient should be taken in a suitable sense under certain topology. So here K is a field of Lorentz series, and O is a ring of formal power series. Now for each dominant co-weight, lambda of T, so when I say dominant co-weight, which means I already make a choice of Borel in the algebraic group, I would like to denote T2 lambda to be the image of T under this co-character. So this co-character is from K star to TOK, and TOK is subgroup in GOK. And then I take E2 lambda as the coset T2 lambda GO in the Affine Grassmannian. So this is in fact, this is a T fixed point in the Affine Grassmannian. And then the Affine Schubert variety, G bar lambda, is defined to be the closure of the Affine Schubert cell. So this is again, this is GO orbit at E2 lambda. And there is a decomposition. The Affine Schubert variety, G bar lambda, is a disjoint union of many Affine Schubert cells, and it consists of those cells G mu, so that mu is dominated by lambda. So this is standard partial order. Mu is dominated by lambda, even only if lambda minus mu is a sum of positive co-roots. So first, let me remind you a well-known theorem, I think probably mainly due to Kumar and the Meshu in this affine setting. So let L be a level 1 line bundle of the Affine Grassmannian of G. Then the global section of the line bundle on the Affine Grassmannian of G, and you take the dual, it will be isomorphic to all level 1 integrable, highest order integral representations of the affine Lie algebra. So this L head of G is a affine Lie algebra associated with Lie algebra. And so this decomposition, kappa means a component of Affine Grassmannian. So each component of Affine Grassmannian, it supports a level 1 highest weight module. So this is kind of a Broadway-Bott type of theorem. And for the second one, if we would restrict the line bundle, the level 1 line bundle, to the Affine Schubert variety, and we take global section and then take a dual, it will be the so-called affine Demazure module, level 1 affine Demazure module, for which I denote by D1 lambda. So the lambda will be originally given is a dominant co-weight. So in fact, this affine Demazure module can be defined as the cyclic module of the enveloping algebra of GOT. So this is the current algebra at this V lambda. V lambda is certain extreme wave vector in this highest weight module. Okay, and then I want to tell a theorem originally due to Evans and Milkovich, and there's also nice proof by Markin, Ostrich, and Ribanov, which asserts that the smooth locus of Affine Schubert variety is a big cell, G lambda. So in the proof of Markin, Ostrich, Ribanov, they use many techniques. For example, they use Stanbridge, some combinatorial results on the dominant weight, and they make some Levy reduction, and they use the Casares polynomial Affine Schubert varieties. And they also use Kumar criterion for smoothness. They combine various techniques. And for us, we are going to do something different. Our goal is to determine the smooth locus of twisted Affine Schubert varieties. And so this is our main criterion we are going to use. So giving a smooth variety X and an action of the torus, the fixed point, the fixed point subskin will be still smooth, right? If original variety is smooth with action of torus, and then the T fixed point, the subskin is still smooth. In other words, if we want to tell a variety is smooth or not, but in particular at a certain point, it's just really enough to look at its T fixed point is smooth or not. Right? This again, this is a T fixed point subskin. So this method is actually initiated in a paper by Xingwen Zhu in the setting of untwisted Affine Schubert variety. So it basically didn't really give a new result, but this method is going to be used by us for the twisted case. Okay, now I can state a theorem. It is referred to be the duality theorem for level 1 Affine Demazure module, and coordinate ring of this T fixed point subskin on the Affine Schubert varieties. So giving a dominant co-weight lambda, we can consider the restriction map from global space of global sessions of the line bundle on this Affine Schubert variety to its T fixed point subskin. So this is going to be an isomorphism when G is of type A and Dn, in this case due to Zhu. And in the case of E6, well, Zhu proved some partial result and fully proved by Bessie and myself this year. Well, it's pretty complicated and based on some partial result method of Zhu. And also, Grimshaw helped to verify proposition using Sage math. So yeah, we get help from some others. Okay, so here I want to make a remark is that, so this T fixed point of the Affine Guasmania, it is the underlying set is a finite set, but it may have a highly non-trivial, non-reduced structure, but it is affine. So since this is an affine scheme, and you take a global sessional line bundle on this affine scheme, and it will be isomorph to coordinate ring of this T fixed point subscheme. So this is why we call it the duality theorem, because on this side, the dual of this this H0 G lambda bar L is Demazure module, and on this side, this is a coordinate ring. So in this sense, we call the duality theorem. And from this theorem and some simple fact of the Affine Demazure module. So when mu is strictly dominated by lambda, then so this is a, as I said, this is a T fixed point subskin, it has support consists of fundamental point E2 mu. The mu will be dominated by lambda, right? So this is the component support at E2 mu, and this part is the sub component of skin has a non-trivial, non-reduced structure. And if you take the coordinate ring, it turns out this guy is just the weight space of the Affine Demazure module. And so this is Yoda. So first of all, this Affine Demazure module is a module over the current algebra GOT. So the weight, I mean H weight, H is the Cardan subalgebra in G. So this Yoda is a map from the co-weight lattice to the dual of the Lie algebra. So it means it will transfer the co-weight to weight. Okay, so and then you put the minus. So again, this dimension will be equal to the dimension of the weight space of the Demazure module. By pretty simple Affine Demazure module theory, this dimension will be greater than 2. And since the underlying reduced structure, it consists of finite set, but the dimension of this skin is greater than 2. So it means this point will be a singular point. Okay, this is what I'm trying to say. The theorem implies that E2 mu is a singular point, and it gives a proof of the theorem of Ivan Mikhailovich when G is of type AN, Dn is 6. In fact, there's another interesting application of the previous theorem. Let me go back. So this map is isomorphism, has interesting application, which is called the Hikita conjecture, a subject related to symplectic duality. So this theorem due to Kamnitzer, Tingley, Webster, Whips, and Jacobi. So it really based on the previous isomorphism. When G is type AN, Dn is 6, the coordinate ring is actually isomorph the cohomology ring of certain Nakajima variety. Let me not get into the detail of which variety it is. So in their paper, they actually claim for all type of simply lace type, but that's not exactly correct because the isomorphism is still not known for type E7 and E8. Okay, now this is special Perholowski. Now let me start to talk about the twistor story. So for let sigma be a standard morphism of order M on G preserved in the Borel subgroup in the torus T. So when G is not A to L, so the sigma is just a diagonal morphism. And if G is not type A to L, it's a diagonal morphism, sorry. And in the case of A to L, and sigma is slightly different, it's not exact diagonal morphism, it'll be order 4. And then we can define the action of sigma on this field. Okay, and the ring O. So basically it means sigma will preserve C invariant and the sigma X on T by multiplying this primitive root of unity, the M primitive root of unity. So here I assume sigma has order M. So, and then O by will be sigma fixed point on this ring. Now let head G sigma be the central extension of the twistor loop algebra GT, and then take sigma fixed point. So because sigma on G and also X on T, so we can take the diagonal actions and then we can have standard construction of twist affine Lie algebra as a central extension of this twistor loop algebra, which appear in the book of Katz, chapter 8. So we call it standard really because this fixed point subalgebra G sigma is that a standard final part of this twistor affine Lie algebra. And now we want to define a group scheme over this O bar. O bar is a sigma fixed point ring. So it can be defined as a group functor giving any O bar algebra R. It is sent to G over O times R over O bar. Then you take sigma fixed point. So again, sigma X on O and X on G. So we can, again, can have a combined action sigma on this group. So this will be represented by a group scheme of O bar, which we call this G. And so this group scheme is actually smooth over O bar, and in fact it's called a special periodic group scheme in literature. So in the sense of Varieties. And if we take an O bar point for this group scheme, then you will exactly get a GO and take a sigma fixed point. So in a sense, we just trying to make it a scheme structure for this group over O bar. So in general, special periodic scheme of twistor type correspond to special vertices on affine Duycken diagram of twist types. So this colored vertices are all special vertices, and this blue one will be the one we have taken care of. So we start with a standard diagram morphism, and then we get a group periodic group scheme over O bar. Then it will correspond to this blue vertices. And for this green one, one can get it by taking diagonal morphism in the case of type A to L. Okay. So for this green one, actually this special one, actually Haynes and Richard call this vertex absolutely special. Now we can define the affine Grassmann of this periodic group scheme as the quotient. So this is a loop group scheme, and this is the jet group scheme. And again, the quotient will be taken in a Schubert sense. So let's not get into the precise definition. Instead, I can tell what is a C point. So if you take C point, then you will get a GK sigma quotient by GO sigma. And then we can call this, in this sense, we can call it the twist affine Grassmann. Now, I want to, so first of all, sigma again is originally is a diagonal, so is a standard morphism on G, preserving a Borel torus. So it induces action on the coordinate lattice X low style T. And so we have the projection map X low style T to X low style T called sigma coinvariant. And so X low style T plus is a set of dominant coordinates in X low style T. Okay, so this means dominant coordinate, and we can take the image in this sigma coinvariant, and then the image will be denoted by X low star T sub sigma and plus. So this is notation. For any element for any co-weight lambda, originally I already explained in the very beginning, we have this T2 lambda, right? A point in GOK. Now I want to cook up a sigma invariant element in GOK. Okay, I want to land here. So we can take the so-called norm over T2 lambda. You take sigma I, and then X on T2 lambda, and then take their product. So this is norm map. So the norm of T2 lambda. After you do this, and then it will be land in GOK sigma. And then we take the coset, right coset in this case, and lambda and GO sigma, okay, and lambda GO sigma. So this is going to be a point in left coset, sorry. So this is a point in the twist Affine Grassmannia. And I will denote by E2 lambda bar. So lambda bar means the image of lambda in x logs dot OT sigma. The point I can denote by E2 lambda bar because this point does not depend on the choices of x log or lambda in here. So it only depends on the image lambda bar. Then the twist Affine Schubert variety is a closure of the Schubert cell. Okay, is a closure of the Schubert cell to the Schubert cell in this case. And then we similarly have the decomposition. The twist Affine Schubert variety will be disjoint union of many other twist Schubert cells, G mu bar. Okay, and mu bar is dominated by lambda. I mean, under this closure relation, exactly when the difference lambda bar minus mu bar is a positive sum of image of symbol colloid Fi check. So here Fi check is a set of symbol colloid of G in x log of T. So right, so one can regard Fi check to be element in x log of T. So I want to make a remark to explain more conceptually about this closure relation. Jiuzu proved a version of geometrical Satake correspondence for this periodical scheme, a special periodical scheme. He proved that the category of purpose shift, spherical purpose shift on Affine Grassmannia is equivalent to representation category of a certain algebraic group H. So H is the lambda group of G, and you take a tau fixed point, and this tau is a diagonal morphism associated to sigma. Okay, so one can think in this way. So sigma you written as a product of diagonal morphism and inner part, and this diagonal morphism is that corresponding to sigma. And under this correspondence, everything can be explained. So, for example, lambda bar in the image x log of T plus sigma actually is a dominant weight of H, and Fi check bar will be simple root of this algebraic group H. Okay? So H will be actually will be reductive group, of course. So again, we always assume G to be a joint type. In this case, we also can describe the component of the twist Affine Grassmannia. So this is the data we start with, type ADE, and then M is the order of these standard automorphisms. Then this is the covariant lattice, and then quotient of the lattice or collude lattice, Q check. Okay, so and then you take co-invariant. So this exactly the component exactly parameterized by the element in this co-invariant. So for example, type A to L minus 1, and then order is 2. Then there are 2 components. So in the case of A to L and order 4, and then there's only 1 component, and so forth. So again, in the twist case, we also have Brodie-Bott and type theorem. So let L be a level 1 line bundle on the twist Affine Grassmannia. Then similarly, you take global section, space of global sections, or this L on the twist Affine Grassmannia, take a dual, it will be exactly the same as on twist case. It will be there sum of all level 1 highest weight integrable modules. So now in this case, it should be twisted Affine algebra. So here there is a typo. It should be L head G sigma. Okay, so it will be twist Affine algebra, and so each comma will be support on the component G comma. They're the same as usual. And if you take global section of this line bundle on the twist Affine Schubert variety, then you will recover a Demazure module over the twist current algebra GT sigma. So this is twist current algebra. If we take enveloping algebra, and then the twist Demazure module will be realized as the cyclic module of this enveloping algebra, twist current algebra at V lambda bar. So this V lambda bar will be certain extremal wave vector in one of these highest weight integral module. Okay, so I can state basically the main theorem, I think, one of the main theorem. So let lambda bar be any element in this X low style T plus sigma. Okay. So it's image of a dominant coordinate in here. So if this periodic scheme is not type A to L, twist A to L, then the smooth locus of twist affine Schubert variety is that a big cell? Is that similar to the theorem of Evans-Mikhowicz? And if G is of type A to L, twist A to L, then the smooth, so for the standard type, then the smooth locus of the twist affine Schubert variety it will be the union of the big cell, and possibly it will consist of some other cell, G mu bar. And this can be completely determined by combinatorics. Yeah, let me not get into the precise combinatoric here. So then let me make some remark. So when this periodic scheme is absolutely special, I mean, this is labeled by the green vertex. In the case of type A2L2, the smooth locus of this twist affine Schubert variety, bar lambda bar, is that the open cell, and this is due to Richards. And he basically used the argument of Mikhowicz, Ostrich-Webanov. And in fact, our method is not applicable in this case because there is no level 1 line bundle on the twist affine Grassmannia when this periodic scheme is ever special, I mean, green vertex, because our we only consider blue vertexes. And on the other hand, yeah, so, okay, let me mention. So part 1 of this theorem, together with the result of Richards in this special case, will fully confirm a conjecture of Haynes and Richards. So basically, this is exactly the case whose smooth locus has big cell, okay? Now, for part 2, I mean, this theorem, this is already beyond the conjecture by Haynes and Richards because it's more complicated, and we are able to determine the smooth locus completely. And there's another remark that by some argument of Haynes Richards, in fact, our theorem will also hold over a field of good characteristic. For example, finite field, right? If you have some mild resolution on the characteristics, then this theorem also holds for any good characteristics. So the theorem I just mentioned will follow from as I said at the beginning, one can get a new proof of Evans-Mikhowicz theorem by using the simple criterion. I mean, use the duality theorem of type AN, DN, E6. So similarly, for the twist case, we are going to do similar thing. We are going to follow similar strategy. So the theorem I just explained will follow from a similar dual theorem for the periodic scheme. Okay, so this is a theorem I want to explain. So for L be a level 1 line bundle on the twist affine Grassmannia, and then we restrict this level 1 line bundle to the twist affine Schubert varieties. And this on this twist Schubert varieties, in fact, we have action of the this torus T sigma. I mean, T is the maximum torus, right? In G, and you can take a sigma fixed point, and we still get the torus. And then we take and this torus acts on the twist Schubert varieties, and then we get the fixed point subscheme, and we consider the restriction map. So this restriction map is always isomorphism without any restriction for any G. We started with a standard automorphism, and then we construct a periodical scheme or bar. Okay. So this theorem, once this theorem holds, then we immediately, not immediately, at least immediately we get part 1 of this theorem, but for part 2, we need some more effort. Okay, we also need to use some argument, actually more precisely, the V reduction argument or Markin, Austrian, Vibanov. Okay, and we also need to crucially use some result due to Haynes Richard in the case of twist A2. Okay, again, here we really use similar strategy, right? To determine which fixed point is smooth or not, we just look at the dimensional coordinate ring of this fixed point subscheme supported at this E2 mu bar. Okay, so this is E2 mu bar. So this is a point in the twist affine Grassmannian. And it turns out if mu bar is strictly dominated by lambda bar, the dimension will be greater than 2, right? Because this dimension is equal to the dimension of the wave space of this affine Demazure or the twist current algebra. So this, again, giving a mu bar, we can transfer it to a weight of this H sigma, okay? Sigma fixed point on this Cardan side algebra H. So here, firstly, on this side, you have x log dot T mapped to x log dot T sigma. And on the other side, you can take a restriction map, okay? So originally, we denote this map by Yoda, and then it will descend to the map on the bottom level, okay? And give a mu bar here, then we get a weight here. Yeah, the reason that the case of twist A2L is more complicated because this dominant relation does not necessarily imply the dominant relation on this weight side, okay? So, as I said, in most cases, if the group scheme is not twist A2L, then any smooth locus of the Schubert variety will be the big cell. And this is not true for twist A2L. There is an example, for example, when lambda bar is quasi-minuscule, then, so quasi-minuscule means 0 is also dominant, right? Basically, there is only one dominant way is dominated by lambda bar, which is 0. Okay, so in this case, the Schubert variety is smooth. It has 2 cells in this Schubert varieties, but it is smooth. Okay, let me remind you actually another interesting application of the duality theorem for the twist type. In fact, from the duality theorem here, if you make a lambda bar to be more and more dominant, and then this side you will recover H0 GL, okay? So which means this will be basically their sum of the. So if you take dual this side, then you will get their sum of level 1 highest weight, indigo highest weight modules of the twisted affine algebra. And on this side, in fact, if you take let lambda bar become more and more dominant, and this side will be isomorphic to Affine-Grassmann, this twisted torus. Okay, and this side will exactly gives you the Fock space of Heisenberg algebra L hat H sigma. So I mean, this is really just the twisted version of non-twisted case, right? In a non-twisted case, you would take gross section of the line bundle on Affine-Grassmann. It will be isomorphic to the line bundle on this Affine-Grassmann torus. So this is spirit torus and this is non-spirit torus. Okay, so similar. So this non-spirit torus is pretty similar. Yeah, it will be, should be, yeah, it is regarded as a torus in this periodical scheme. Okay, now let me explain the strategy, how we get our duality theorem. So our duality theorem is a twist type. We prove this duality theorem by using some global methods. So basically, we build a family of Affine-Grassmann. Generically, it will be usual Affine-Grassmann, and at the 0, let's say we have A1, let's say. At 0, it will be twist Affine-Grassmann. And in fact, we have a global version of Schubert varieties. Generically, it will be usual Affine-Schubert variety. And at 0, this special point, the fiber will be twist Affine-Schubert varieties. Okay, now first let me introduce something called this global object called the Varieties group scheme. It will be either defined over P1 or A1. So let me first start with P1. So let P1 be the pressure line with coordinate T. And I would like to introduce a sigma action on this pressure line. Just map T to P multiplied by this primitive root unit as usual. And now let P1 bar be the quotient. Okay? In fact, this P1 bar is also isomorphic to P1, of course. To distinguish the original P1, we'll use P1 bar. Now we can define the following group scheme over P1 bar. So this will be defined as a Weil reduction of the constant group scheme on P1 and then reduce to P1 bar, and then you take sigma fixed point. Okay, so instead of telling you the precise definition of this periodical scheme over P1 bar, let me describe some properties of this group scheme over P1 bar. So when over the point, which is not 0 and infinity in P1 bar, the reduction of this periodical scheme of this group scheme to the formal disk around the Y, it will be isomorphic to a constant group scheme, okay? Just G times dy. And when Y is 0 in P1 bar, and then if we restrict our group scheme, we just constructed to a formal neighborhood of 0, then it will be exactly the periodical scheme we discussed earlier. Okay. So which means we get a family of groups. So yeah, we have a group scheme over P1 bar. At different point, we get our familiar objects. And at infinity, we also get similar periodic group scheme. Okay? Similar. And such a group scheme over P1 bar is called a Varieties group scheme in literature. Now, one can do the geometry on this Varieties group scheme. So let bound G to be modular stack of G tossers on P1 bar. And the geometry of this bound G has been studied recently by many people, including Papa Rapport, Heinrich, Jiuzu, Balaji, Shaji, and myself and Kuma, and so on, okay, in different settings. Now let me explain some ingredients for the duality theorem for the local periodic group scheme. So one can construct the global Affine Grassmannian or this Varieties group scheme or P1. Okay. So let me tell a C point of this global Affine Grassmannian. The C point consists of triple. So it'll be P will be a point in P1, and F will be a G-tosser, okay, similar to vector bundle. And alpha is a trivialization of this G-tosser outside. It will be, again, F is a G-tosser actually on P1 bar, okay? P1 bar is a quotient of P1, and P bar is the image of P in P1 bar. So F, the trivialization will be on P1 bar, excluding P bar. And this global Affine Grassmannian, if you take the zero fiber, the fiber at zero will exactly get a twist Affine Grassmannian. And if you take the fiber at outside zero and infinity, we also get we exactly get the usual Affine Grassmannian. Okay. So at least when, sorry. So there is a natural forgetful map from this global Affine Grassmannian to bound G, okay, the stack, algebraic stack. This is just forgetful map, right? We have triple just map to the middle guy. Middle guy will be a point in this bound G. And on the other hand, by Heinlo's uniformity theorem, there is also a quotient G map to. So this is the twisted Affine Grassmannian, okay, the local one. Will also map, subjectively map to bound G. Okay, so this is global. And to be honest, to do this kind of geometry, we first better to assume G is simply connected. Okay. So we want to construct level 1 line bundle on this global Affine Grassmannian. So this is not totally trivial thing to get it. So the approach is that we first want to construct a level 1 line bundle on bound G, and then we'll pull back to, pull back to here. Okay, this is a strategy. First, we have a level 1 line bundle on the twisted Affine Grassmannian, and then we want to prove it will descend to the level 1 line bundle on bound G, and then we'll pull back to a global Affine Grassmannian under this forgetful map. So now the point is how we construct level 1 line bundle on bound G. We are going to use some argument due to Soldier. We compute twisted conformal block, which now vanish, and somehow then one can prove level 1 line bundle exists on bound G. Okay. So there's a remark that the theory of twisted conformal blocks has recently been developed in more general setting by myself and Kuma. But here we only do some special case, and it's pretty computable in this special case. And another ingredient that one can construct so-called global Schubert varieties, which will be flat over P1, so that the fiber at 0 will be the twisted Affine Schubert variety. And outside the 0 and infinity, we'll get G bar lambda. Okay, so generically we get G lambda bar. Usual Affine Schubert variety G bar lambda, and at 0 we get G bar lambda bar. Okay, and again lambda bar will be the image of lambda in the sigma co-invariant. And then this is how two versions of duality theorem are related. So again, we already have duality theorem for type AN, DN, E6 in the untwisted case. And by this global method, so in fact, we can prove the duality theorem also holds for our special periodic group schemes. And let me make some more remark. So this basically is the the proof of why the duality theorem holds, and then from the duality theorem for the paragraph scheme, it implies the smooth locus of twisted Affine Schubert varieties. So finally, let me make some remark. Once we have the line bundle L on this bound G, and then, so this is exactly how the geometry or line bundle, the globalization of line bundle on bound G is related to twist conformal block. So let me take L is a level 1 line bundle, and take 6 tensor power, and you take global sections on bound G, and then take a dual. And then this will be isomorphic to, so this side is really space of twist conformal block. Let me know, yeah. So, okay, this is level C, integral representations of twisted Affine algebra. Also associated to 0 weight or G sigma. So, in particular, in fact, one can, by this identification, then one can show dimension is 0, bound G, L is 1, in fact. And another remark is that in a ongoing joint work with my student, another student, Huang Yu, we are developing the theory of a twisted global Demazure module, and we are able to identify this twisted global Demazure module with line bundle on so-called Jiuzu Schubert varieties. So when n is 1, this is just the global Schubert variety I just mentioned in the previous page, but one can, in fact, one can define Jiuzu Schubert varieties for type of dominant weight. Then this is more complicated object. Okay, so this is basically what I want to talk about. Thank you.